We've seen how to use integration to calculate areas of patches. We can also use integration in a very similar way to find volumes of solids. The idea is when we're finding areas, we sliced up that area into a bunch of infinitesimally thin rectangles and then added them all up using integration. With volumes, we can do the same if we consider the volume sliced into infinitesimally thin sheets. If we know the area of each sheet as a function, a of x, then the volume of that is the integral over those sheets, which means it's the integral of the area function times the infinitesimal width of that area. This we can think of as the integral over some infinitesimal volumes dv, giving us the total volume. So this is perhaps easier to see on a picture where it's sliced into widths of width delta x, and then we let delta x go to 0. The easiest way to understand this process is to work through a few examples. Let's begin with the example of finding the volume of a pyramid. Let's take a pyramid with a square base, and let's say that square base has a side length L and a height h. How do we go about finding the volume of that? Well, let's first draw a diagram to see what's required of us. So we're after finding the volume of an object like this. Let's just label the lengths. The length of the base is L and the height is h. How do we go about finding the volume of this? Well, the idea is to slice this up into slices where I can calculate the area of each slice in a systematic way. Then adding up those slices will give me the overall volume of the object. So what I'm going to do is choose a slice parallel to the base. So I choose a slice parallel to the base, and that slices a pyramid which gives me a square, and that square I can calculate the area of. In order to see this, let's try and coordinatize the problem as follows. I'm going to lay the pyramid on its side, where x is going to measure the length from the tip of the pyramid towards the base. So I lay it on its side, and then I can work out the area of that square. So the square cuts through the pyramid. The distance to that slice be x units from the top of the pyramid. This length here, L. What else do I know? Well, I know that the height of this pyramid overall is h, and this base length is L. Okay, so now I've set up a coordinate system to represent the problem. The area of the slice is just little l squared, but that in itself isn't particularly useful. What I need to do is represent that in terms of x, because what I'm going to do is add up all of the slices as I move from x equals 0 to x equals h, the height of the pyramid. Now, using similar triangles, the ratio of x to the height of the overall pyramid is the same as little l over big L. So this implies, and this tells me then, that my area function as a function of x is L squared, which is the constant L over h squared times x squared. And this is a key step. So the volume is now the sum over these slices. If each slice has an infinitesimal thickness dx, a of x times dx is the infinitesimal volume of a slice. Integrating over those from 0 to h will give me the volume of the pyramid. The rest is now just calculation, and this comes out to be. So that's an example of using integration to find a volume of a solid. There are many ways we can go about this sort of thing. And again, it's probably easiest to do this with an example. Let's try finding the volume of a sphere from first principles using integration. Let's find the volume of a sphere of radius r. Now, again, it's not immediately obvious how we're going to go about this. But let's start with a circle. In fact, let's start with a semicircle with the equation y equals the square root of r squared minus x squared, as usual. Now what I'm going to do is a slightly strange thing. I'm going to rotate this circle in my mind around the x-axis. So I'm going to rotate it around the x-axis like this. And as we take that curve, rotate it around the x-axis, it's going to trace out a sphere in 3 dimensions. So now I've got my sphere in 3 dimensions. I'm going to keep that in my mind's eye, but keep this 2-dimensional drawing as a reference with which to calculate the area function and then the volume. I'll keep a side-on view of my sphere, and now what I'm going to do is slice this up parallel to the y-axis. So let me take a slice through this sphere like this. So I'm going to slice it up in the same way that I did the pyramid, in a way that makes the calculation straightforward. And let's have a look at this slice. So this slice is a circle, and the radius of this slice is not r, it's going to be given by the function height y. So the radius of this circle then is y. And the area of that slice then is just pi y squared. Now if we consider this thing to have an infinitesimal thickness, which I'll draw schematically like this, and if this thickness is dx, then I can think of the infinitesimal volume, the disk, is pi y squared dx. So I take this circle, imagine it has an infinitesimal depth dx. Now the volume is going to be given by the sum of slices from minus r to r. And so, given that they're infinitesimal, that sum becomes an integral, which is then the integral from minus r to r of pi times r squared minus x squared. And then the rest is just calculation. Because the integrand is even, I can write this as 2 times the integral from 0 to r, and then integrating term by term, I get, which comes out to be 4/3 pi r cubed, as expected. Now, that last example for a sphere is an example of a solid of revolution. I took the function curve and rotated it around the x-axis to produce something where if I take a slice parallel to the y-axis, I get a circle. So this is a method of finding volumes of solids of revolution through this conceptual trick of rotating it around the x-axis in our mind's eye. In fact, we can find the volume of many solids in this way. Let's try an example of this, which brings out a solid of revolution with a hollow part in it. Let's find the volume of the solid formed by rotating the region trapped between y equals x and y equals x squared around the x-axis. Let's find the volume of that solid. First thing to do is to draw a diagram to see what the question's asking. So if I have my xy plane, the function y equals x, which I'll call y1, and y equals x squared, which I'll call y2, then if I'm going to rotate this around the x-axis, that's going to give me a shape which looks a bit like a cone, but the center of it will be hollowed out. How do I find the volume of such a thing? Well, again, we're going to slice this up. So let's consider a slice, and we'll try and find the infinitesimal volume of this slice. Again, let's let it have thickness dx. Now, how do we go about that? Well, if I imagine rotating it round the x-axis, this thing is going to give me a disk with a hole in it, an annulus. If I can find the area of that annulus, then I can integrate over that area function to find the volume of the solid of revolution. So let's just label on what we know. The radius to the outer disk is just y1, and the radius to the inner disk is just y2. And so the area is just the difference in the outer circle area minus the inner circle area. And so the volume is just the integral from where the curves cross, which is at 0 and 1, times pi y1 squared minus pi y2 squared. I integrate this over dx. I can now substitute for both functions. So y1 is equal to x and y2 is equal to x squared. And again, the rest is just a straightforward integral to calculate. And so this comes out to be. So this general idea then allows us to find the volume of any sort of object which has a circular symmetry. One can lay it out in a coordinate system which is appropriate to that, slice it up into circles or disks like we did in the last example, and integrate over those area functions to find the volume.